Good morning, good afternoon, and good evening, depending upon where you live around the world. You might pick up from my tone of voice that I'm in quite a jovial mood. That's because I started with a very arrogant way of saying certain things in my mind. When I hear it, I'm going, yeah, that's confident, yeah. And I started to then dissolve in front of or in the face of the reality of trying to build something. I shoot myself in the foot quite regularly. I had made the comment about getting a accuracy down to the 1/10 of 1 degree for our hub design. Now, remembering that this is a piece of garden furniture basically, or garden architecture, that doesn't require that level of precision or accuracy. But not wishing to build in inaccuracies from the get-go, which can multiply, and I do wonder whether is some of the problems that I've heard about with people building geodesic domes. I like to have the theory as close to correct as possible, and the real world ability to build something follow closely on the tails of that theory. Example, when I built at my probably second house, I do most of the plans of the houses I build on myself. I got down to the last millimetre where the placement of the studs and twangs were. Now, years later, I could actually go back to that same house. It was actually my friend, instructor, friend Alistair, his house, and we could go back years later and find exactly where items were in that house because we did the work initially to draw the plans accurately. Was it necessary? No. But being that anal retentive perfectionist person that I thought I was, I did it anyway. Let's move on. One of the things that I did wrong was that I started building the models and I made a bit of a boo-boo, let's say. I had to then correct it. And all this time, I was creating all these very accurate angles. They're dead, well, accurate down to the last 10th of a degree. But I knew that at some stage I was going to have to replicate this onto the hub. Okay, so I can take some of these angles and I'm just going to write them down, and I'll just jot them down so I can refer to them, so don't go away, which I've now done on a bit of paper, because I had to think of a way of achieving the drilling of the holes with this sort of accuracy. So come with me. We come to this. Have you ever heard me say I overthink things, or that I work myself into a dead end? Well, I kind of did with this. This is a derivation of a woodworking project that I'd designed many years ago, and this is the latest iteration of it, where I wanted to get down to, what was it? 1/10 of 1 degree, which each one of these lines is 1/10 of 1 degree. This is 5 degrees, this is 10 degrees. It's on a board that's 600 in radius. It's got a 600 radius here, the radius and circumference. And what happens there is, if you want to, you can actually print this out, because after all, SketchUp will draw something accurately, and you can print this out and you can combine it on multiple sheets of A4. And if you go to Matthias Wandell's website, he's got a program called, I think, Big Print, or Large Print, or Big Print, where you can join multiple sheets into one accurately large format or combination. And you can print it out, stick it, sticky spray to a piece of melamine or some such, and create a big protractor where you could move around and mark your plates. I thought, well, that's good. But then I was having difficulty figuring out where that had to go. So I started having a wee bit of a think. And think as I might, I started working on the fact that when I measured, we'll get back to this in a moment, when I measured the distance from one line to the other, it was about 1 millimetre. And I'm going, oh, that's interesting. If we can mark around a arc like this, I was just trying to think what you call it, a piece of custom wood created in this shape, a pie, a quarter of a circle, we could mark off just simply with a tape measure every X number of millimetres to get our desired degrees. Now we don't have to mark every 1 millimetre, because around a circle this big there's 3,600 marks, because I'll progress, otherwise it's going to take too long. But what's interesting is that if you made a disc or a quarter of a circle with a radius of 572 millimetres, so we're going to call it 573, each millimetre would be 1/10 of 1 degree. Interesting. So in quick order you could find out that, say I wanted 61.3 degrees, which is one of the angles we had on our model earlier in that honeycomb model. Well, we only have to work out how many. Well, that's probably going to be 613 millimetres. So we could work out, just using a tape measure around the outside, where our 61.3 degree line is. You could mark that and scribe it on your disc. Come round, we want 56.7 degrees. Well, that would be 567 millimetres. And then I thought, that's a really good idea. So I'd started out, and this is the progression, with a disc at 600, because I thought, why not? It's economical to build and relatively still small. But if you build it with a radius of 572 or 573, every millimetre or a specific degree. So let's go do that. I'll pause now and I'll replicate a quarter disc with a radius of 573. So just wait there. So there we have a quarter disc at 573. Now, if we use this well, we can measure around with our tape measure as accurate as we're able to do, and it would have to be a fairly flexible tape measure. Every 1 millimetre would be the 1/10 of 1 degree. Okay, repeating myself. But if we only want the 61.3, we measure around 613 millimetres. Seems reasonable. You can make a full disc, but that's getting just ridiculous. But every time you want to do this, you could add and subtract 90 degrees or whatever to get the correct angle. Now, I started going down the rabbit hole, and I thought, it's still, even listening to what I've just said, you might be lost, and you go, well, okay, the logic's sound. Instead of having all these darn lines drawn out, I thought, well, you just need the 6 that you need for your hub. So what's that? Okay, I'll pause again and I'll come back. And back again with what we've got here is a circle. This happens to be 57.15 drawn accurately with SketchUp. Won't be able to measure that, but trust me, that's 57.15 in radius. These two lines are 60 degrees between them, accurately drawn with SketchUp. But the next line, is 56.1. So I'm going to rotate it 56.1, because down in the bottom right hand corner, and there we have it, 56.1. that's accurately drawn. We won't be able to measure that, which is a bit of a shame really, but hey, I can rotate this one 56.1 because it's symmetrical through the vertical center line here. What's the next one? Well, I just happen to know that. That happens to be 56.7. So 56.7 degrees, and we go. And of course, you guessed it, we're going to rotate this one round 56.7. And in the middle, between these two, should be 61.3. Now, I'm going to rotate it, and we're not going to be able to read it out accurately, but if I rotate it round, we've got 74.4. So what's the inaccuracy here? I'm going to tell you what it is. It's because we're working on a flat surface, and flat surfaces aren't what we're working on when we're looking at a dome. And I'll just draw back in the other, because here, and this is what threw me when I was drawing some of them, and why you've got to do these in plane. These angles are inclined angles. So when you lift them up into a flat plane, they read differently. I got caught when I was actually drawing it, and I go, I didn't know that. So what we need to do here is generate these measurements or these angles as a flat surface. And that's because you think about it, if the reason a dome's a dome is that when you fold items together or triangles together, they pucker up and create that dome-like structure. Duh, of course it is. So in another drawing, I've actually created these with the correct angles, which I have to find, and I don't know where the heck I've put it on my computer, but nonetheless, that's how accurately you can draw a line within SketchUp on a circumference. As I say, I'd have to find the other drawing, which I haven't got loaded at the moment, so excuse me. But then you can print this out on an A4 sheet, stick it to a piece of wood or onto your metal, and mark off the positions for these lines. 6 lines. The distance between each line or the angle is going to be precise, and it's on a size of a tube or marking of your desired dimension. So this tube here could have the paper sat on it, and you just have to etch the marks down onto your face of your tube. Or if it's the disc, same sort of thing. You make your pattern the size of your disc, and you can perhaps center pop the marks. Now they're going to be as accurate as we can physically manipulate it, other than getting it laser cut, which is probably the preferred option for me. If you want to spend a few dollars and get it done dead accurately, then it saves a whole lot of drama, because after all, you have to cut the steel tubes accurately and nice and square and etc., and the plates nice and round or whatever shape you decide upon. So if you're going to get them cut by a laser company, why not just get them marked and the centers cut out at the same time? But one of the things was I wanted to be able to create the accurate models within a home workshop. So that we can do that means that I've achieved one of the goals of this project. After all, some people might not want to go to the extent of this accuracy, but having a method to get it pretty darn accurate, it's not a bad thing to have up your sleeve, so when you're building it. Okay, so that's where we're at here. The other one is, I'm actually coming back with a part 2, and we'll look at I'm just going to say, an even better way. Okay, I will leave you with that tidbit, and I will see you in the next video. Bye.